Yeah. So, hi everyone. Thanks Harpreet for a wonderful presentation. Thanks Jimmy for hosting this event as well. Um, I'm Raghav, and I'll be presenting something about the GUI agents, but a bit more in detail. So we'll be talking about more on the foundational capabilities rather than just agents as a whole. So what Harpreet mentioned was a very general level, high level talk about how the agent landscape is panning in today's world. And indeed, it's a fast growing space, but at the same time, only building agents and kind of only handling all the computer related tasks is one aspect of it, while the other aspect of it is kind of doing more like a foundational groundwork and building models that are actually able to understand what the computer screens actually mean. So with that, I would like to present this talk, which is more on the foundational capabilities of the models, which actually drive those generalist agents. So until now, the space that we are in, we have like a lot of multimodal agents. We have action model learning. We have automating computer interaction systems, which kind of interact with different applications and websites and kind of drive all the computer related tasks. Again, like this is essentially very important for all the digital accessibility for people who are technologically handicapped. But at the same time, it's also very important that going forward, we kind of more and more rely on these tools as they not only make your life easier, but also makes it more efficient. So with that, I would like to present one of my papers, which I presented at ECCV pretty recently. It's been gaining some traction. It's called the OmniACT. What we did was a data set and a benchmark for enabling multimodal generalist agents. And these agents not only work for the web, which a lot of common agents are doing right now, but it also works for the desktop applications, the native applications, so works more on the operating system level rather than just working on the web. And this work was done by me and a few of my colleagues during my time at Carnegie Mellon. And this was again in association with one of the leading AI startups in this space. They have pretty recently launched also an agent which kind of works for all the creative tasks. This company is called writer.com. So we closely collaborated and partnered with them to get the OmniAct data set and the benchmarks. So let's dive into it. So basically, the task is that given a screen and a task description, which is represented by a tuple S and a T, the output should be directly a code script that can actually be executable and run that particular action. So how this is different from a traditional agent is that a traditional agent is given a lot of retries. So let's say it's not able to um, get the execution right in the correct time or in the first attempt. It's actually allowed to retry and perform a different action like humans do. But retry and reattempting is, I mean, decently fine, but this doesn't show that the person has or the agent has grounded or like a sound knowledge of the domain. So our aim here is to build foundational capabilities or like the more fundamental capabilities to develop that kind of knowledge to actually drive the agent to perfectly execute the action without any retries. So given this, what we see here are a few examples. Let's say you have a stock application where I just ask you that check the rate of change in Google stock price over the last 1 month. So instead of performing or like breaking the action into multiple parts, what it should rather do is like generate a direct RPA or like a process automation script that can actually execute the task. So this requires multiple things. One is code understanding, one is screen understanding, one is task understanding. So a lot of these things kind of go in this entire system. And the initial results that we actually saw were pretty shocking. And then as we kept on improving on it, we actually saw that improving these foundational capabilities is a much important task than just building the agents. So there are a lot of prior works, there are more recent works as well, and a lot of these works cover different aspects. So for us, the main highlight for this was that it works on desktop and web, which means it's basically acting on all domains and environments. It's task heterogeneous, like it has like a different set of tasks. It replays like a real world scenario. We also focus on executional correctness. We support desktop apps. We have a continuous adaptation scale. So even in the evaluation space, what Harpreet mentioned, explainability is kind of a big problem as of today. So OmniACT also tackles that, and we'll be going deeper into it pretty shortly. So let's dive into how we actually collected the data. So starting from a data perspective, we first selected a few websites and applications. This was across like the top categories like shopping, government, information, travel, health, entertainment. And again, we selected a few native apps from each of the operating systems. So the coverage is again the Mac OS, Linux, Windows. We also have a few websites. So we do take in Chrome and a few browsers. Once that is done, we kind of segment the UI screens. So for every application, we take a couple of screens. Using those screens, we kind of annotate them. So these are done by professional annotators with a lot of experience using different operating systems and kind of doing the annotation tasks. So once they create the bounding boxes and label them, we then move on to the third step, which is the functionality tagging. So functionality tagging is more of how that bounding box is supposed to perform, or like what is the function of that bounding box. So let's say you have an example from the iBooks app. So here what we do is that we have a section called the book of code red. So we kind of annotate them with specific labels performing like different actions. Once that is done, we give it to another set of annotators, which is, which are more um, adapted to kind of building these tasks. And also they have sound knowledge of code. So they basically take in those functionality tags and kind of create tasks from the screens. So one of the tasks could be, I want to open this book and flip a few pages and underline something. So these tasks are then represented in the form of code, and these things are then executed and filtered, which is part of our last step. And also the tags that we had created are converted into specific coordinates so that they become executable. At the end of the day, what we have is a lot of samples with all the samples having some kind of executable code, which actually drives the agent end to end. So now we talk about the desktop first. So going into the desktop, we have 110 plus screens. We took 40 plus applications across three operating systems. All the annotation was done on a PyQt5 custom tool. At that time, a lot of these sophisticated tools were not present, so we had to come up with our own. The annotators are then asked to create diverse and natural tasks which are actually executable. Also, based on all of this, we kind of get like around 8,000 standard data points. These are all gold standard, and all of them are ensured for executability. Yeah, so after this, let's dive into the operating systems and what we chose. So Mac OS had around 20 applications or so. Windows again had 12 native applications. Linux had 8. All of them combined, we kind of ensured that the applications that we are selecting are also different in nature, so that the coverage is not only operating system based but also task based. Then for web, again, we select like a few categories. Based on the few categories, we employ a script that kind of creates bounding boxes along with their functionalities. Once that is done, we again send these to our annotators who kind of annotate them and get the labeling and the correct functionality tags for each of the bounding boxes. As you see that this process is kind of pretty time taking, but at the same time, it's also, I mean, very important because it also ensures the quality. And without a good quality data set, the agent will only learn how to mess things up while execution. So this data set is kind of a gold standard data set in that respect. Yeah, so this is like an exhaustive list. Also, another point to note is that we also ensure in this data set that all the tasks that are performed are only performed within a single screen, which means that all the actions are done within 3 to 5 steps. How that helps us is that building on smaller tasks actually gives it a perspective of how to plan it and kind of execute a long horizon task in a better way. So our goal in this paper was to create fundamental tasks for the agent and not train it on a complete end-to-end task. So if you're talking about booking a flight ticket from Paris to Singapore, that task will essentially be broken into the different screens that we have. And then every screen is then executed on its own in a native environment, and then the actions are kind of combined. So once we have like a few gold label data sets, we move on to the augmentation. Augmentation was a big initiative in this data set. We had a lot of task diversification using LLMs. So synthetic data was one of the, key drivers of how the model was learning. We use Palmyra X, which is a writer's native model, and that was actually performing pretty well because of its nature and creativity. Another diversification that we did was in terms of language. So language again is a key driver because not all tasks are, represented in the same way. Also, the annotators or the humans are prone to kind of using the same language again and again. So the same task can actually be represented in two different types. And each of those types, or I would say, different questions can be then fed into the LLM to train it in a different manner. So what is 2 plus 3 can also be represented as calculate the sum of 2 and 3 or add 2 and 3. And these things are, pretty helpful for the model to learn. Um, yeah, so before I go forward, yeah. So one last thing I wanted to discuss about was the data set statistics. So in the end, we had like around 9,800 data points, out of which we split it into the standard training, validation, and test. We observed that the mouse clicks were the maximum. We also supported multiple actions. And these actions are, pretty much exhaustive. From what I see in the other literature, I don't see any other paper kind of or any other work kind of incorporating so many actions. So we have like all the actions ranging from double clicks, right clicks, moves, hovers, drag, scrolls, horizontal scrolls. Same for keyboards. We also support hotkey presses like the shortcuts Control A, Control C, all those things, and again writing in the text box, pressing different keys. So we support a bunch of actions here as well. Most of the agents that we talk about are more like web agents, and they kind of operate on clicks and I mean some kind of write. But with our data set being introduced in the industry, people have actually started exploring a lot of other options like horizontal scroll, because at the end of the day, the agent has to perform in the most efficient manner. So if you want to copy your file, doing a right click, then doing a copy is kind of harder than just selecting a file and doing a control C. So this is what the aim was. Before I move on to the next section, I would pause here, see if you have any questions. Yeah, so I see one question by Prabhat. What would be the high-level use cases are you planning by building this agent? Yeah, so basically the plan is actually to build a brain for all the agents. So what we want is that this fundamental model should be incorporated in all the agentic systems that are building. So until now, all the agents that we are seeing are kind of more or less dependent only purely on LLMs. That kind of reduces the explainability. Um, but this agent is more for a desktop agent. So there is a recent startup or a product that's actually working on it. It's called the Vercept AI, and they are building agents for the desktop. So, I mean, companies like these or projects like these can actually benefit from models like OmniACT. So that's the high level goal. Moving into the dataset analysis, so once we had all the data in place, um, we kind of did some kind of attention heat mapping to see which part of the screens were actually being used. From what we see in today's world is that for desktops, the usage is pretty concentrated towards either the center of the screens or towards the bottom corners of the screen. The reason is that most of the buttons and the I mean, interactive elements are present in this part of the screen. Whereas for web, we have links all around. So here, if you see, we have like a bunch of, I mean, different regions that are kind of lit. Also, we see that the bottom right and the bottom left is also pretty much highlighted. This is because generally the next moving forward previous buttons are kind of here. So these kind of drive the attention maps accordingly. Yeah, I can take one more question. Yeah, that's it. Um, Yeah, so someone is asking, could you use a separate agent, not necessarily visual, to break the complex task into? Yeah, that can definitely be done. So what we are doing, and I'll go through it in a while. So what we are doing is also basically dividing a big task into multiple smaller tasks, and then kind of I mean, initiating our agent on top of it. So those agents can definitely be different from the visual agents because they require more of a planning. So that can be like a agent which is good at a long horizon planning task. Yeah, so once the data set was built, I mean, the next logical step was to solve it, to have some kind of benchmark. When we use some VLMs without training and directly using them just by prompting, we saw that the results are not very good. Probably the things are not grounded, and eventually the performance degrades. Also, the components and the buttons, how Harpreet was also showing, are pretty small as compared to the screen size. So what happens is that it's unable to detect a lot of times what is happening in the UI. So standard VLMs kind of often fail in those cases. So we first decided to logically extract the meaningful information out of it. So first was using the detect module. So this was a custom module that we created on our own. This has three layers. First is the OCR layer, then we have the icon matching module and the color module. So OCR extracts all the text-based elements. We then use SAM 2.0 to segment the screen into different parts. These segmented screens are then mapped onto the icon elements, and we have like a icon matching pack that we had curated and that we use to match if we have any relevant icons. So let's say a calendar icon would definitely signal dates, or a bell icon would signify notifications, or a location icon would signify the place. So similar to that, we wanted to observe all the visual cues. And the third is the color cues. So generally, like a stop button would be red in color, or the continue or a play button would be green in color. So things like that are often determined by the cues. Same with how you expand, minimize, or close your screen. Even those have set colors. So a lot of times you don't have to actually read the label. Rather, you can just see the color and figure out what exactly that interactive element is supposed to do. So that was the idea behind all these. So the way this detect module is panned out is that whenever you get a task, let's say here it's something like click on the black location icon and enter the destination as Paris. What it will try to do is that first it will extract all the text-based elements from the OCR module along with its coordinates. The next, it will also segment the screen using the SAM 2.0. It will then figure out all the icons and the location where different colored elements are present. These all go into an LLM-based filters to get only the relevant ones that we are supposed to do based on our task. So let's say for this task, going to location icon and black button are one of the key elements that we want to interact with. So this is what the detect module will give out. Generally, what happens is that whenever you are using a web-based browser, you generally have a HTML DOM model, which is unavailable in desktop apps, which is why this step becomes definitely more important. For desktop and native apps, you kind of need to have a visual element rather than just relying on the text-based HTML DOMs. So this is the core idea of it. So once you do that, so once you do that, we use those things and pass it into our models. Those models are ranging from fine-tuned LLMs to standard VLMs to fine-tuned VLMs, and we'll go about all these results in a while. But before that, I wanted to dive more into how we are evaluating the performance. So agentic performance is generally measured in execution. So it's either a zero or a one based on whether the task was executed or not. But oftentimes this shadows the explainability part of it, which is actually necessary to understand where the agent is going wrong. So we decided that we should open up this metric and kind of split it into different parameters so that we actually understand where the agent is going wrong. So when we talk about the metric, we first understand whether it's able to whether the agent is able to plan it well or not. So if it's able to plan it well, in that case, we give a sequence score. Sequence score determines whether you were able to plan your actions in a correct sequence or not. So let's say you wanted to click on the blue button and type something on the screen. So ideal movement of your cursor should be to click and then to write. So if you are able to perform it, or like not even perform but even plan it correctly, in that case the predicted action sequence is correct and we give like a higher score to that. So for our use case, we took beta 1 as 0.1 and beta 2 as 1, and S is the length of the sequence. So basically, how this math is working is that for longer sequences, we are giving them higher points. So if it's just a one-step process, we are just giving it 0.1. Whereas if it's a five-step process or a six-step process, we are giving it 5.1, which is a lot more score. So how this distributes in a longer range is that the sequences which are predicted correctly and were also longer are kind of rewarded higher. Once we have the sequence score, we want to see how well it actually performed. So that is something called the action score. So action score is the performance that you got on how you planned versus how you executed. So once you have planned correctly, you also can make a lot of mistakes. Each of these mistakes is then penalized by some or the other penalty. So we have three sets of penalties. One is the mouse penalty, which is basically that which is also, I mean, called the click penalty, which is basically that you clicked at a wrong location. So we have like a bounding box over all the elements which we got from our annotations. And whenever we see that the click was outside the correct bounding box, we penalize it in the form of a Dirichlet pair. And this is how we are penalizing it. The math representations are on the right. So the higher or the farther you go from the actual bounding box center, the more it will penalize. Same for the key penalty. So key penalty is when you press the wrong key. So let's say you had to press space or enter and you press something else. So this is a direct match. So you cannot just afford to press Control V when you have to press Control C. So in that case, it's a binary evaluation. And then we have a right score which penalizes for anything that you have written incorrectly. So let's say you had to write Singapore and you wrote something like Malaysia or Paris. So in that case, again, like it's semantically entirely different. What we want is more of a thing that actually makes sense. So here we are calculating the blue score. So blue score kind of determines whether semantically it was closer or farther. So combine these scores, we kind of penalize from the sequence score or the planning score that we have in the beginning to get the action score. And then we normalize it on the basis of, I mean, the the scores that we are getting. And based on this, like we get the final score. So how this is integrated into the baselines and how the entire system pans out is something like this. So you get a task and an image, and you have a task, which is something like right click to copy link from C deals in the Expedia email, and then you have a screen of Expedia email opened in the email application. This goes in the detect module. The relevant elements are detected. We have a structured prompt, I mean, template that we kind of use. This is then passed into the LLM to finally generate the script. So these were our baselines that we tried. We tried a bunch of baselines by prompting LLMs, fine-tuning LLMs, fine-tuning VLMs, and then finally using things like GPT-4o, Gemini, and here were the results. As you see here, we can also see the sequence score, the action score. Um, these metrics kind of tell you how frequent or how prone is the model to actually make those mistakes. So this opens up the execution metric that we had previously and kind of tells you where it is going wrong. So let's say if we see the GPT 404V version, this had a sequence score of 38.72, which means it's pretty good in planning, but at the same time, it does a lot of mistakes in clicking the bounding box or identifying the coordinates or writing or probably pressing the right key. So this reduces its total to 17. So action score is kind of normalized, which we can see here. Um, the human performance is kind of on 80. The latest models that we have tried, and apologies, this is like a bit of an old paper based on how the speed of the domain is actually progressing. It's been like a few months, but the newer models and the newer agents that are coming up, so those are also not up to the mark. They have reached a level of somewhere around 40-ish on the action score that we are calculating, but it's still far from the human performance. Um, yeah, a few more things to that we kind of observed were like how impactful was the detect module, and we saw that when we tried GPT-4o with and without the detect module, there was a drastic difference in how the action score worked. So sequence score, if you see, is pretty much the same, which means that it's good in planning in either cases. The detect module is not very helpful for planning, but it's helpful for execution. It's helpful for identifying the right parts of the screen to interact with, which is why you see a major bump in the action score right here. Same for ablations, like the other ablation, which is we wanted to see how the sequence length works with the performance. So we see that the shorter tasks are pretty easy to perform, whereas as you kind of go further, you'll see that longer tasks are, I mean, harder to perform. So probably we saw that there is a need of some kind of long horizon planning models which can actually do that. So with this, we come to the multimodal transformer that we actually, I mean, devised after trying on all the baselines. We decided that the standard LLMs are not working very well, and there is a need that we have to kind of build our own model. So what we did here was that given a screen image, we use the detect module to get the screen annotated automatically. We also use the pixel level information, and based on that pixel level information and the entire screen, we input this, or like we give this as our training data or the visual cue. And same for the natural language instruction, which is just, I mean, converted into an embedding and sent to this encoder. Based on these two combined, we have a continued pre-training of this pre-trained multimodal encoder, and we do a cross-modal alignment using a couple of different objectives. So one is the contrastive loss and one is the ITM loss. Both are derived from the GIVL paper. And the approximate size of training that we did for the action model was around 70 billion. And then we use a standard decoder, which is more like a code generation model to finally get the output scripts and then run it through the executor. We saw that these results are much more promising. The results for using the multimodal encoders are close to 40 on the action score, which is much better than the standard VLMs that we have today. Yeah. Thanks a lot, everyone. And I'm open to any questions that you have.
I think there was one question, maybe I'll summarize it more broadly, which is, have you had an opportunity to take a look at some of the latest drops from OpenAI? And if so, do you have any opinion on how that may affect the landscape and the work that you're focused on?
Yeah, definitely. So I have seen those agents and they're working pretty well. I see that. I also tried like their latest models on the OmniACT. I mean, the results are improving day by day. I still see like a lot of open issues, especially again in like the fundamental capabilities. Primarily because the UI grounding is not at that level. I feel like the agent might be able to perform or like plan the task very well, but then during the time of lower level execution is where it actually goes wrong. Although I mean there is a significant progress, but the time taken for execution, the planning that goes behind it, the number of retries that the agent has to do. I think all those things can still be cut down if the foundational capabilities are more thought of.